Learning Measure TV, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com.
Episode 34, Mixing the Mixed Signals.
Hello, I'm David Archer. I'm owner of LearningMeasure.tv and LearningMeasure.com. LearningMeasure.com is a subscription-based training service where when you sign up, you get 1 week free, and then for access to all the courses, it's $5 a month after that. As we talked about last time, I'm doing a series on signals and their measurement. Today, we're going to talk about a device that's used in a lot of measurement systems and something used to measure a lot of different types of signals. And that device is the mixer. The symbol for a mixer is a circle with an X in it. So what a mixer basically does is multiplies two signals. That's why there's an X there. So if you had some signal here, and you had another signal in here, let's see, let's call this V1. This is V2. What comes out is V1 times V2, basically. Well, that's not entirely true, but it's close enough for what we're going to talk about now. In particular, a mixer, you might want to put some sort of sine wave input into a mixer, maybe two sine wave inputs. Okay, and we're going to label these ports. We're going to call this the RF port, call this the LO port, and this is called the IF port. Radio frequency, local oscillator, intermediate frequency. We'll explain what that means in a minute. So let's say this is some signal that's of the form V1 sine omega 1 t, let's say no initial phase. And let's say this signal here is V2 sine omega 2 t. Well, what comes out? Well, the product of these. So that would be V1, V2, sine omega 1 t times sine omega 2 t. Well, some of you may remember your trigonometric identities, that if you have something like sine theta 1 times sine theta 2, that's equal to 1/2 cosine theta 1 plus theta 2 plus 1/2 cosine theta 1 minus theta 2. That's just a trig identity. Okay. Well, let's apply that trig identity to this. So what you come out with is V1, V2 times cosine of omega 1 plus omega 2 t plus cosine omega 1 minus omega 2 t. Now, another thing you can know from trig, so sine theta plus pi over 2 radians equals cosine theta. So what comes out, I'll do it over here, is V1, V2 times, well, there's a 1/2 over 2, times the sine of omega 1 plus omega 2 t plus pi over 2 plus sine omega 1 minus omega 2 t plus pi over 2. So what comes out of the mixer, you got two frequencies going in, and what comes out are two sinusoids, one at the sum of the frequencies and one at the difference of the frequencies. That's kind of what, so if these were the same frequency, you'd get a DC component and something that was twice the frequency, for instance. You could use this one way, you could double the frequency. So both these signals are in the output. This is why mixers are often called frequency translation devices, because what they do, we put two sinusoidal, two frequencies in. What comes out is an output that has the sum and the difference of those frequencies. Now, there are also, since mixers aren't ideal, there are all kinds of harmonics there, products of the harmonics, all kinds of weird stuff that comes out. But that's, by the way, we're not going to talk about how you make such a thing, what constitutes a mixer, just what you do with them. So now that you know from mixer you get sum and difference frequencies, let's say we talked about AM last time. So where you have an AM signal, which is V of t times some amplitude sine omega t. Well, you could generate that by putting your V of t, you could, it's not usually done this way. Well, maybe it is sometimes. And you can put in your A sine omega t. And what comes out, right, is your V of t sine omega t. Sine omega t. Well, what could you do with that? Well, you could put this out to, let's say, an antenna, and you can call it an AM radio broadcast transmitter. So what's the other way around? Well, what if you wanted to receive an AM radio broadcast? And you have something that's coming into your antenna, which is some V of t sine omega carrier t. We'll just call it omega c. Well, what you can do is run that after. You'll probably do some things like you'll amplify it, among other things, and then you'll maybe stick it into a mixer. And here, into your mixer, you'll put in a local oscillator at frequency that's something like sine omega ct. Well, then what comes out of here is the sum and difference frequency, so you get something in it. So what you get is something that looks like V of t plus V of t times sine 2 omega t, okay, plus some phase. So what you can do after that, well, let's put something in here, a low-pass filter that knocks out this term. And what you come out with is V of t. So you basically have made an AM radio. You down convert, recover the information. There's more stuff here and there's more stuff here, but that's the basic idea of an AM radio. So mixers can be used for lots of things. This is called demodulation. And then there are anytime you want to make a measurement of a RF signal or a AC signal, it's generally the case that the lower the frequency, the more accurate your measurement's going to be. I have a little tangled up in my cord here. Sorry about that. So you might want to measure some, let's say, frequency of something. You have a frequency counter. Let's say you wanted to measure 5 gigahertz, and you only had a counter that could measure frequencies out to, oh, I don't know, 100 megahertz, let's say. Well, what thing you can do, well, you have your 5 gigahertz signal. Wow, it's getting dark all of a sudden. And you can mix that down by putting in something like a signal, that's locked to a stable oscillator at 5, let's say 0.01 gigahertz. And then you put out another low pass filter, and what comes out is your 5.01 minus 5 gigahertz signal. Well, a 5-ish signal, right? You don't know exactly what it is. So you can count that with your frequency counter. Now, of course, making a measurement like that, this is just an example of what you could do with a mixer. There are all kinds of problems here. There's frequency components here, there's errors here, there's errors here. If this is stable, unstable, weird things can happen. But in general, you can use a mixer in all kinds of situations. And next time, this is going to be a real short one. Next time, we're going to discuss what you can use, a particular measurement that uses a mixer. Just wanted to spend a short episode talking about what a mixer is and what it does. And then we'll talk about some specific measurements of signals that you use a mixer for. All right, that's it for this short episode. Again, if you have any suggestions on what type of topic you want to see covered here, send us an email at suggestions@learningmeasure.tv. If you have a question, send a question at questions@learningmeasure.tv. And if you want to be on the podcast for any reason, if you want to sell something or make a presentation, even if you want to put yourself out there for your services out there for other people to use, send us an email at vendors@learningmeasure.tv. Thanks, and that's it for this short episode. I'll see you next time.